All right, here we go. Photoelectric effect, part 2 in the modern physics video set. So you should have already done the gizmo on photoelectric effect. That was assigned to you already. If you did not already do that before watching this video, because it's important that you investigate it a little bit yourself and start to understand it a little bit more before I formally instruct you on it. So what the photoelectric effect proved and showed, if we have specific waves coming in at specific frequencies, specific intensity, it doesn't matter. When they come in and they hit an object, we notice that a few electrons will bounce off. A few electrons will become liberated. Now, what caused this to happen? Well, Einstein came together, and Einstein started thinking a little bit more about the photoelectric effect, and he used Planck's ideas to show that the photoelectric effect was caused based on specific frequencies and specific energy levels freeing those electrons, sort of like they were held prisoner but needed a specific amount of energy. So if we took a really, really low frequency and we bombarded it as much as possible against that surface, no electrons were let out. But as soon as we get that frequency up to a specific level, enough so that way it could start liberating these, once we cranked up the intensity, then we could see more and more start flowing. So it doesn't matter about the intensity, it doesn't matter how much of these waves we send at it, it needs specific frequency or specific energy to allow it to release. Also, take a look at this joke. Photon checks into a hotel. The bellhop asks, "Can I help you with your luggage?" It replies, "I don't have any luggage. I'm traveling light." That's what a photon is described as, traveling light. I know you don't think that's funny, but I do, so we'll move on. Okay? So what we noticed was light is made up of particles called photons. Whoa, 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 take a second. Light's made up of particles. But when we spoke about polarization and diffraction, we knew that light was a wave. Wait. This was the argument that these physicists were having around this time. Some would say it's a wave, some would say it's a particle, and they would go back and forth and they'd argue each other. Well, it turns out neither of them were true. Light is not a particle, light is not a wave, and light is not both a particle and a wave. What light is light has properties of both a wave and a particle. Light has properties of a wave and a particle. It's called the wave-particle duality. So it's important that on the Regents test and the test that you see in the future, if you're asked any question about what light is not a wave and a particle. It's not a wave and it's not a particle, but it experiences properties of both. So that's where the duality comes in. And to formalize it a little bit more, we got this handy-dandy chart. So when we look at reflection, well, we could have a wave and a particle reflect, so that doesn't prove anything. Refraction, we could have a wave and a particle refract. Remember, refraction is how the source, whether it's a wave or a particle, how it interacts within a changing medium. We notice it slows down, the wavelength may increase, a bunch of things may happen, but we notice that it occurs both in waves and particles. Interference. Well, interference only happens in waves, not in particles. Diffraction, again, only in waves, not in particles. Polarization, only in waves, not in particles. But for the photoelectric effect, this was the first time that we saw that, okay, it doesn't occur in waves, but it does occur in particles. So if you're studying for an exam or anything like that, take a look at this chart, because you're going to be asked questions on maybe which phenomenon proves that light is a wave, or which prove that it's a particle, or which show that it could be either. So it's important to take a look at this and to recognize and to understand that there's a bunch of different phenomenon that help to show wave-like and particle-like properties. playing with some of the settings. Okay. So the photoelectric effect, it showed us that an increase in frequency increased the energy that we were able to see. I don't like this setup. Let's just give it to you. So within our waves unit, I want to say it's like the 6th or so equation down. We learned that, or we now know, that the energy of a photon is related to, remember this is Planck's constant, so we're going to need to know this, Planck's constant times the frequency. So each individual photon has this much energy. That's why we call it the energy of a photon. And if we break apart frequency, we know that velocity is equal to wavelength times frequency. Well, for all light, we know that velocity is equal to c. So this whole thing is equal to wavelength times frequency. And if we bring frequency on its own, we learn that frequency is equal to the speed of light divided by its wavelength. So we take this and we make it substitution. So now we have two separate equations to try to figure out the energy of a photon. Whether they give us the frequency, we use this equation. If they give us the wavelength, we're going to use this equation. So we got a couple equations for modern. Let's jump into some practice problems. Take this time now and try to solve this problem. So pause it, go for it. Okay, you worked on it already. Let's go through it. Check your answers. So first thing we do, rewrite the equation. So they give us yellow light in terms of a frequency. So we're going to use our equation for energy in terms of a frequency. Step number 2, we're going to plug in our givens, or the numbers that we know, including units. So we're going to use our Planck's constant, the 6.63 times 10 to the negative 34th, and we keep our units, a joule times a second. It's important to use this unit because we'll notice that the hertz, which is equal to 1 over seconds, will cancel out with the seconds here. And our final answer, drum roll, 3.38 times 10 to the negative 19 joules. So what I want to challenge you now is I want you to convert this from joules into electron volts. And we already know how to do that. So we're going to get 2.11 electron volts. Okay? Small amount of electron volts, but it makes sense. Let's try another practice problem. Okay, try this one out. Go ahead, try it out. Okay, we're back. So, this time they're asking us for the energy of a photon. So we're automatically thinking we want to look at a photon. Well, which one are we going to choose? This time it gives us in terms of a wavelength. So we're going to use the wavelength equation. We're going to rewrite the whole thing. We're going to plug it in with our units and our givens. Okay? We got Planck's constant. We got the speed of light in a vacuum or in air. We divide by our wavelength. And we get 3.8 times 10 to the negative 19. Well, those of you smart people out there, you knew what my next question was going to be. Convert it into electron volts. Go ahead. And we do that conversion. We get 2.38 electron volts. So these are going to be a lot of this is going to be similar questions to what you're going to receive on tests that I give you and on the Regents test. So make sure you're familiar with this. Make sure you know how to choose whether it's a wavelength or whether it's a frequency, and make sure that you can plug in like this. So if you didn't do these practice questions, do the practice questions now.